Okay, so today we will study linear filtering of long duration sequences. Okay, we are curious how this linear filtering of long duration sequence, how it is different for than shorter duration sequences. Like, linear filtering is nothing but linear convolution. Let me clarify. And we want to do this thing using DFT. Okay. So not in time domain. We are bothered about doing these things in frequency domain. So I had already convinced you that there is this algorithm called as fast Fourier transform, which will let us do DFT very, very efficiently, right? N by 2 log n number of multiplications. So that's why instead of doing it directly in the formula x of k h of n minus k, which is there for linear convolution, so doing it in using FFT algorithm is much more efficient, which we'll realize later sometimes. Okay. So that is why let us discuss what is this linear filtering using DFT first. So what is the catch involved, by the way? Linear filtering can be done using, that means DFT usually gives us, see this particular thing, right? This particular thing, multiplication in the frequency domain in the DTFT would give us linear convolution, but in DFT, the multiplication in the frequency domain usually gives us the circular convolution, right? It gives us the circular convolution. But then we have solved one or two problems. One of them was your homework also. We have found out that if at all we choose the value of n point DFT, right? DFT comes with this n. Okay. If at all I choose the value of n is equal to length of the first sequence plus length of the second sequence minus 1, right? Then we get the answer of circular convolution same as that for linear convolution. Okay. I hope you might have understood this particular thing. Okay, because what is happening in circular convolution, I have told you previously, what is happening is actually when you say circular convolution, it is the result of linear convolution only, but all the values. Okay, can you hear me? Namrata, you can hear me? You can hear me, right? Okay. So what is happening in circular convolution? Suppose I say 4-point circular convolution, all the values after 4 are getting overlapped, or the right word the textbook fellows are using is aliasing. Okay, you can see here, if at all I say 4-point circular convolution, this 2 and 1, they are getting added up, you get circular convolution. If at all I do 5-point circular convolution, this 1 gets added up. So the idea was to choose this length, not to choose this length equal to length of the first sequence plus length of the second sequence minus 1. And when we do that, even the answer that of the multiplication in DFTs and take the inverse, we will still get the answer same as that of linear convolution or linear filtering. So the bottom line, digital computers can be used to perform linear convolution using Fourier analysis. Okay, using Fourier analysis. Okay, that is the idea. So circular convolution is a byproduct, and what we want is linear convolution. Very much possible. And here is the method. Usually in the textbooks, what they do is the length of the input is represented by L, and the length of the impulse response H of n, this is usually represented by M. Now let me clarify that usually the length of the sequence is even only when doing in our text books examples, we take x of n equal to 3, 4 and so and so, but actual length is usually very large. Okay, before going to that, let us do this particular thing here. It's a time exercise. Okay, so here is an example. By means of DFT IDFT method, determine the response of the FR filter. Response of a filter means this is the input. This input goes into the filter whose impulse response is this. Okay, that's the thing. Okay, that means we want output. Okay, so response of an FR filter is x of n convolved with h of n. Okay, it's the linear convolution of these two. So what we have to do? So here we have to, but DFT does only circular convolution. So what we have to do is, here we have to choose our n is equal to length of the first sequence 3 plus length of the second sequence 4 minus 1. Okay, so this here length equal to, this is my m, not my m, our m. Okay, Length of the impulse response is usually taken as M. Length of the input is taken as L. If at all I choose N is equal to how much? 3 plus 4 minus 1, 6. If at all I take 6 point DFT of first sequence, 6 point DFT of second sequence, I multiply, take 6 point IDFT, that's it, I'm done. I will get the answer same as that of linear convolution here. Okay, fine, everything is fine. But when we come to the real world scenario, what actually happens is real world data is very, very long. Okay, so for an example, if at all I have to tell, suppose I am speaking to you something, and say at the end of the day while posting, say I want to use some video tool, I want to upload it on YouTube, I want to use some processing tool, and say I'm having an audio of say 5 seconds. Say I'm having an audio of say 5 seconds, and if at all my audio clarity is say, even if it is telephone quality, a telephone quality is very ordinary quality, then for a telephone quality, usually the standard is per second. Telephone quality means per second 8K samples. Telephone quality means per second 8K samples. If at all it is MP3 quality, then per second 16,000 samples. So that means if at all I have to filter a 5-second data, 5-second data, how many number of samples it's going to contain? How many number of samples it's going to contain? Then if at all I say whatever I am processing now, whatever I am speaking, if you want to filter it and then you want to send it over a wire, okay, and if at all I say it's a 5-second data sampled at 8K, right, you know, right, continuous data is sampled, made into discrete. Say my sampling frequency is 8,000, then for 5 seconds I need how much amount of data? How many number of samples will be there? How many number of samples will be there for 5 seconds? Then can anybody tell me? The data rate is 8 kbps, 8 kilo, no, 8,000 samples per second. Then if at all data is sampled at 8,000 samples per second, if at all there is 5-second data, whatever I'm speaking, 5-second audio, what will be the total number of samples? Can anybody tell me? Can anybody tell me? So what's the number? It's very good. Okay, 40,000 samples. Okay, so I only misled you in this. Okay, it's not kbps. A kb, the small b, usually it is bits. Okay, here let me clarify. Usually in audio clarity, one sample is 8 bits. Okay, so that's 40k into 8. Okay, so let us talk about samples. So I have totally 40,000 samples per second. Okay, we have totally 40,000 samples. What is the textbook story we do here? See, I will take usually x of n equal to 4, 5, 8 maximum, right? Because you have to solve the numerical. Okay, it's not possible. Actually, the length of my input can be anything from just for a single second. It's going to be minimum 8,000 samples per second, and maximum for the audio clarity. Okay, audio CDs you might have seen, right? Audio CDs, for that 44,000 samples per second. That's the amount of data that needs to be processed, filtered. Okay, I had shown you the equalizer. Remember, I had shown you once in VLC player the equalizer. It's a filtering thing. Okay, what about the length of the impulse response? Length of the impulse response is usually, we will realize it's not 2 or 3, but usually it will be something like, order of the filter will be something like 40 or 50. 40, 50, 80, something like that. Okay, 40, 50 or 80. But do you realize the huge gap you can see? X of n is somewhere around 4,000, how much? 40,000, 80,000, 1 lakh and all. Whereas H of n is something like only 40, 50, 80. That is the filter length, H of n length. So how do you do this? How do you do the linear filtering? How do you do the linear filtering? Okay, that is the first catch. Okay, so what comes to your mind is whatever the thing I told you. Okay, length of the first sequence plus length of the second sequence minus 1 if at all you take, and then you do the circular convolution. What you get is linear convolution. Fine, everything fine. But now you remember, you have to suppose the who is that Prime Minister is making a speech on 15th August, and it is on live transmission. Okay, if at all I go by this particular method, so what is it, by the way? We have to accumulate all the data. If Prime Minister speaks for 1 hour, then we have to accumulate all the data for 1 hour. You can imagine how many number of samples per second. 16,000 samples. 1 hour, you can imagine number of samples. Filter order is something like 20, 30, 40 or 50. But then Live relay is not possible, right? If at all you want to accumulate all the data at once, stuff in the zeros by zero padding, and then want to convolve, it's not possible. Okay. So live transmission is not possible if at all you go by the conventional method that we studied just now. And the second thing is, even if you want to zero pad, here in this particular example itself, let me tell you, here, see that this particular length is, I have chosen the total value of n that I need to choose is something like 15. Okay. That is like 15. Okay. So length of this sequence is only 10. So here I need to insert 1, 2, 3 zeros I need to pad. Whereas here I need to pad another 12 zeros. 12 zeros. And then I have to take 15-point convolution for the first sequence, DFT for first sequence, 15-point DFT for second sequence. For first sequence, there is 225 multiplications. For second sequence also, another 225 multiplications. Then you have to multiply x of n with h of n. That's another 15 multiplication. Then you have to take IDFT. So this 225 into 3 plus 15, that's a lot of multiplications. Okay. Now imagine the situation, if at all it's a 5-second audio, then there will be 40,000 samples. Okay. So no, we are going the wrong way. I think there is something wrong. So for long duration sequences, I don't think, okay, the conventional method works. So what can we do, by the way? What can we do? We want to do a live relay. Then we do not want to, we want to reduce the number of multiplications. Of course, it's not actually n square, but it is n by 2 log n. Okay, because we can use the fast Fourier transform. Still, now suppose, say, if at all it's a live relay, we don't know. If at all it's a live relay, we don't know PM is going to speak for half an hour, 1 hour, or 2 hours. We really don't know. But we want the data to be transmitted within a delay of 1 second or 2 seconds. It's a live transmission. We cannot wait for the entire thing to end. So what shall we do? What shall we do? Can somebody tell me? What shall we do? Say this particular length, let me exaggerate. This particular length is something like 80,000 samples here. You see, this is only 15 or 12. Say this is 80,000 samples. Okay, this is only 3. What shall we do? We want to do a live transmission. We cannot wait for all the data to accumulate and then we have to transmit. No, it's not possible. What shall we do? Anybody? Any idea? Any suggestions? Let us see. Whatever you are thinking, whether it matches with that of the author or not. Anybody? Any idea? Live transmission. We want to do a live transmission, but the data is never stopping. X of n never stops. What shall we do? What shall we do? Anybody? Any ideas? What shall we do? Anybody want to participate? Shall I tell you the solution, or you have an idea? Anybody? Okay, give up, right? So the idea is, so that's the catch involved. Okay, the long duration sequences. What if, see here, as I told you, say this 15 only, let us say this is 80,000 samples per second. What I will do is, I do not want for all those 80,000 samples to accumulate at a time, because 80,000 samples means even a delay of 2 seconds is still killing me. Okay. Whereas the data is, it's infinite. Let's call x of n length as infinite, because we never know when is it going to stop. Okay. So what we will do is, we will break it into smaller pieces. We will break it into smaller pieces. Piece of 4, right? Shall we do that? We will keep on breaking. As and when 1, 2, 3, 4, some 4 or 5 samples, as and when they are collected, we will simply filter them and will put it at the output, right? Isn't it cool? As and when the data is collected. Now suppose there are some say 100 guests at your home, and say you want to prepare the dosas for them, and they are all sitting on the table. So you will not wait for all 100 dosas to be done at a time. Then you want to serve. No, you have this very small dosa tawa there. At a time, maybe you can put, even in hotels, you can put maybe maximum 8 dosas. So as and when first 8 dosas are processed, you put the masala in it. Let's call it masala as HFN. As and when 8 dosas are prepared, you go on sending them for serving, right? So that's a good idea. Agree, everybody? Not with the dosa thing, but the idea. We'll break it into pieces and let us handle it. It gives us 2 advantages. Okay, it gives us 2 advantages. You can see here, if at all I choose smaller pieces, then I don't have to do much of the zero padding, right? if at all I do take smaller pieces, I don't have to do much of the zero padding, right? See, first sequence length is 4, second sequence length is 3. Then I think this, what is the length? 1, 2, 3, 4 plus 3 minus 1. I need to do only 2 zeros here for this sequence, 3 zeros here for this sequence. I can do circular convolution, still get the answer of linear convolution. Okay, are we cool with it? So do you agree with my solution? Breaking the lengthy input sequence into smaller batches and process them as and when they come, right? This is fixed. Impulse response of the filter is always fixed. Okay, only input as and when they come in the batches of 4 samples. We keep on processing and transmitting them at the output. Okay, fine. Shall we continue? Okay, so here is an idea. Okay, so as I said, let us break it into pieces of 4. See, 1, 2, 0, minus 3, 4, 2, minus 1, 1, minus 2, 3, 2, 1. Okay, let us break it into pieces. Okay, then we will perform circular convolution. Then we will perform, because see, the whole idea here is to use DFT. Okay, we want to do the linear filtering, but in the frequency domain for some advantages which we are not studied. They are there. Okay, so what we'll do? What is this y of n? This y of n is x1 of n convolved with, this is x1 of n convolved with h of n. Okay, what sort of convolution? This is circular convolution. Okay, y1 of n is x1 of n convolved with h of n. Y2 of n is x2 of n. X2 of n convolved with h of n. Okay, what sort of convolution? Once again, circular convolution. Y3 of n is x3 of n convolved with h of n. Now, what should be my length n, by the way? I have to do circular convolution, but my answer should match that of linear convolution. See, what are the length of the pieces which I broke into? 4, right? It's broken into 4. But what is the length of the impulse response? 3. So let me choose n equal to 6. When I do that, my answer of my circular convolution, individual circular convolution, are these: y1 of n, y2 of n, y3 of n. These are individual processed, smaller bits processed. Okay. Now what I will combine them: y1 of n, y2 of n, y3 of n, and there I get my answer. My small question is, just by looking at this particular answer here, just by looking at this, do you think this answer is correct? Is the idea fine? Is it fine? The idea and the answer, by the way, is this answer correct? Is this answer correct? Anybody? Any guesses? Anybody? Any guesses? I am not expecting you to, Rajesh, your video. Rajesh is eating something and is not sharing with anybody. He's going to get a stomach ache now. Okay. Yes. So anybody, let's not get distracted. Anybody, can you tell me, just by looking at this length, of the answer, can anybody guess whether this answer is correct or wrong? What was the length of my input sequence? 12. Length of the impulse response was 3. If at all my linear convolution, if the answer is that of linear convolution, my length of my answer should be 12 plus 3 minus 1, 13, 14, 15. Okay, the answer should have had a length of 15. What do I have here? The length, see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah, yes. So here it is 18. But what is my expected length of the answer? So it is 15. So this answer, unfortunately, is not correct. Our approach is correct. Our approach is correct, but answer is not matching. So what is happening here? So what is happening here is, earlier you have seen, usually when you get linear convolution from circular convolution, you would take length of n is equal to something like this, right, to avoid aliasing. But now let us see the correct answer. So there I have the correct answer here. This is my correct answer, which is done directly. H of n 1 1 1, X of n complete sequence taken. Okay, here is the correct answer. Okay, is it correct by the way? Let us start. 1 3 3 minus 1, yeah, fine. 3 6 3 1, yeah, that's also fine. So where is the missing link? What is happening? Where things are going wrong? Here you can see. See, here there is some problem. 5 and 2 are fine. Here there is some problem. Okay, then where else? 5 and 2 are fine. Then afterwards, yeah, these bubbles, right? See here, 5 and 2 are fine. See here, this bubble here, and let me use, yeah, see these two places. I think there is some mistake. In what way it is? Now see here, what we have to do now to get the correct answer. What if I add these two? See now the problem area. See, okay. Now what we shall do to get the proper answer? Minus 3 plus 4. Minus 3 plus 4 is a plus 1. Minus 3 plus 6 is a plus 3. Okay, okay. Now similarly, which is the second place? Here, here. 0 minus 2 minus 2. 1 plus 1, 2. Okay, that means now somehow the last two values and the first two values of the next segment, these are the segments. Okay, see, these are the segments of 6 what you got earlier. So 6 3 is 18. That was the problem. So we have to do the actual answer. You can see is there is a overlap here. Okay, if at all you do the systematic overlap, maybe we will get the proper answer. That means here we have to introduce some aliasing. We have to introduce some aliasing. So here is the method. So the idea is, let us have the individual sub answers. Let us have the individual sub answer. See, this was the first sub answer, y1 of n. This is y2 of n. This is y3 of n. What author does is he overlaps them. You can see there is an overlapping, right? How many values overlapping? 2 values are overlapping. Okay, 2 values are overlapping. Okay, fine. 2 values are overlapping. And then overlapped values are being added. The overlapped values are added. And when you do that, we get our answer same as that of linear convolution. We get the answer same as that of linear convolution. Okay. So we call this method as, what did we do here? We overlapped and then we added. Okay. So this method of filtering long duration. Now see, the problem is of live relay is now possible. What you have to do is, if at all there is a sequence of 80,000, 3 lakh, 18 Mbps, whatever be the length, how many, whatever, you simply break it into sample length of 20, 30, 40, 50 or 100 and you process them. Only thing what you have to do is, you just have to overlap by factor 2. Now what is this 2 by the way? This actually is my length of the impulse response minus 1. That's the amount of overlap that you need to introduce. Okay, so there is the method. The method is called as overlap add method. Okay, so the method is called as the overlap add method. Okay, so here it is, overlap add method. So how did we do? What did we do here? Let us see this method now formally. Let us see the method formally. So see here, when you do this thing on a computer, on an HDL processor or a microcontroller, you cannot assume things. You have to use fixed processor. So here is the question now. Okay, here is the question. Are you getting this thing by the way? Somebody reply. Are you getting this thing? What did we try to do and did you achieve whatever you wanted to do? Somebody reply. Are you getting this at least partially? Somebody please reply. Okay, so here was the thing. A filter impulse response was given and an unusually large input sequence was given. It was said that you have a computer or a chip. You know chips, right? 7404 those kind of chips, and gate. Okay. Similarly, say you have these chips. The chips are capable of doing circular convolution. Okay. The chips are capable of doing circular. Let's not get diverted from the topics here. Okay. Concentrate. Okay. Concentrate. 12 is compulsory. Okay, okay. Let us see. Let us see. Let us see. Now, say you are given an unusually long sequence. Okay, you are given an unusually long sequence and a small impulse response. Author tells you that you have now chips, hardwired chips, which are having fixed capability to do circular convolution. Okay, DFT chips they are called as. Okay, they comes with fixed sizes, usually 6, 8. Usually they will be power of 2. Okay, 6 is a fictional number which I just took. Okay, usually you will get chips of which can perform DFT. They come in sizes of usually with an FFT algorithm in them. They come with sizes of 8, 16, 64. 8, 16, 64, 256, 512, 1024, and so on. Okay, a radix 2. That's what they are called as. Now here for our example, say author gave us that n has to be, the circular convolution has to be 6. That is the chip size. So what we will have to do when n is 6, n is 6, and length of the impulse response is already 3, then we need n is equal to L plus M, L plus M minus 1. M is 3. Okay. N is already fixed at 6. So what option do we have for L? Anybody? What option do we have for L? It has to be 4, right? So what we will do is, we will break them into pieces of 4. We will break them into pieces of 4. Okay. And last one, if at all there are 3. Then stuff the remaining zeros. How many zeros are we stuffing in? M minus 1 number of zeros. So that the total length of the sequence is 6. Okay. So that the total length of the sequence is 6. Then what we'll do? Then we perform 6-point circular convolution. Then we perform 6-point circular convolution with h of n for each of these. Perform 6-point circular convolution. Okay, either using DFT IDFT method or directly, depends. Okay, how the question is. Usually on computers, it's supposed to be done using DFT IDFT. These are the individual answers. These are the individual answers. Then what we will do is, the last m minus 1 values, the last m minus 1 values of the first sub answer and first m minus 1 value of the next sub answer are overlapped systematically. There you go. Systematically overlapped. They are overlapped and then they are added. So the method. So this particular method is called as overlap add method, used for linear filtering of long duration sequences. Okay. So here is the method. Let us learn that formally. So what we have to do is we break x of n into smaller pieces of length L 0 to L minus 1 is of length L. 4 in our example. Then afterwards add m minus 1 zeros. M, it was 3. M minus 1 is 2 in our example. This was 4. This was 2. Then what do we do? Then do we perform convolution. Then we perform convolution. Either using, it's actually supposed to be done in the frequency domain only. In classrooms, we don't have time. So we will do it directly. Then afterwards, once you get an answer, we just overlap, overlap and add. Okay. Got the method? Got the method? Now, let me ask you, if author says, you have to use n is equal to 8, that means you have to use an 8-point circular convolution only. Okay, because say the chips which are available to perform circular convolution are of length 8. DFT chips are of length 8. Then how many pieces of x of n do you want? And can you tell me the sequences? Can anybody tell me? M is equal to 3 only. Filter is same. N is equal to 8 is given. How do you do it? Can somebody tell me? The rule is you have to stuff in m minus 1 zeros. You have to stuff in m minus 1 sub zeros for individual subsegment, and the total length of the segment shall be 8. Can anybody tell me how many subsegments are we getting, and what is the first subsegment? Anybody? Please participate. Anybody? Anybody? Please participate. By the way, today from 12 to 10 for some 30 minutes, I want to do this introduction to this MATLAB, the lab, and there is one virtual lab. Okay, please attend it. Okay, because I started very late. So afternoons, I don't know whether we'll be busy, free, and all those things. Please attend that thing also. Okay, at 12. I will give you some break also in between. Okay, 12 or 12:10. You tell me time. 12 or 12:10. Do not push it, please. Yes. So will anybody tell me? Want to break it into pieces? Okay. Will anybody tell me what is the sequence? Anybody tell me? Please tell me what are the sequences. I want to break this into pieces. The rule is every subsegment shall have 2 zeros. Total length should be 8. So what should be the length of L, by the way? What should be the length of L? N is equal to L plus M minus 1, L plus M minus 1. M is equal to 3, N is equal to 8. So what is the first segment? Yeah, it is pieces of 6. So first subsegment is 1, 2, 0, minus 3, 4, 2. This is the first subsegment. This is the second subsegment. So can you tell me what is x1 of n? So x1 of n will be 1, 2, 0, 1, 2, 0, minus 3, 4, 2, then 2 more zeros added. Okay. And second sequence will be minus 1, 1, minus 2, 3, 2, 1, then 2 more zeros. That's it. Okay. Then you have to perform 8-point circular convolution. It will be same as that of linear convolution, and then you get the answer. Okay. Then you get the answer. Okay. Fine. Got it. Got it. Everybody got it. Now, let me ask you one more. Say, now, let me ask you one more. Say the author has asked, say my length of impulse response for a change is having a length of 4. Say my impulse response is 1, 2, 1, 1. Okay. Say my input sequence is same. Impulse response is of length 4. And I want to use an 8-point circular convolution. N has to be 8. In such case, what shall be my value of L? What shall be the value of L? What is the formula? N is equal to L plus M minus 1. How many pieces am I getting? Right. Okay. So it is going to be 5. So we will break it into how many pieces? Pieces of 5 each. 3 zeros. So first segment will be 1, 2, 0, minus 3, 4. Then what about remaining values? How many zeros are we stuffing in? Can anybody tell me how many zeros are we stuffing in? How many zeros? This is 5. How many zeros are we stuffing in? N is equal to 8. How many zeros are we stuffing in? Somebody. How many zeros? 3 zeros. Good. You need to subtract 3 zeros. So this is the first segment. Then this one is second one. Okay. Now see here, what about this one? Only 2 segments, 2 and 1 are there. Now what shall we do? Only 2 and 1, only 2 values are there. What shall we do? How many zeros shall we stuff in for this third sequence? How many zeros shall we stuff in for the third sequence? 3 plus another 3. Okay, so totally 6 zeros we shall stuff in. Okay, so tomorrow a small exercise. Okay, so what you do is same example. Say h of n equal to 1 to 1, 1. Okay, just out of curiosity you do it. Okay, say n is equal to 8. Perform the using overlap add method, linear convolution you perform. Then cross verify with directly doing it. Okay. Now there is a small catch involved. Now imagine doing this thing on your microcontroller or HDL. You can see, you will realize as a programmer, inserting zeros on the fly is going to be sort of a tricky situation. Okay. inserting zeros on the fly is not a good idea. Okay, not a good idea. So we need some method where we will go on, manipulating data, so it's so irritating you don't mind, because you can see here, when you are doing it on a computer, whether there are zeros or not, the time is still consumed, the power is still consumed. Okay. So we want to do this entire process without being able to insert, not being able to, without having to insert zeros in between and still get an answer same as that of linear convolution. Okay. So that particular method is called as overlap save method. That's also an interesting method. Okay. So we will see that tomorrow. So now what is the time? 11:54. At 12:10 exactly, I will just call you for one lab session. Okay, introductory session on lab. 12:10 or 12:15. It will be there for not more than 30 minutes. Please join in for that session. Okay. So what just happened? What is the method? The method is, you stuff in, you take the sequence, break it into pieces of length L. Okay. N will be provided to you. N has to be provided. Okay. N has to be provided. Based on that, as per the formula, N equal to L plus M minus 1, you choose, break it into pieces of L, the length L, stuff in M minus 1 zeros, perform N point circular convolution with the impulse response, and then afterwards, perform overlap and add, and you get the answer. Okay. So everybody say hi for this. Okay, I'm sounding creepy there. Yeah, everybody just type in. Type a hi. Okay, I will end it and I will send you an invite. Please join in at 12:15. Okay, so ending this thing.